Hi everyone. I just wanted to swing back to when we were doing the derivatives of trig functions and highlight a couple of ideas and techniques that can be used to solve problems. So we had these derivatives of sine and cosine. So sine went to cosine, and cosine goes to negative sine. And the first thing I wanted to highlight was a nice pattern that comes with this. So if you've got, let's start with sine maybe. I take the derivative of that, we just see above that it's cosine. And I take the derivative of that, we see above that's negative sine. So now I've got negative of a function, and when I take the derivative of negative of a function, I get negative of the derivative. So as sine goes to cosine, negative sine should go to negative cosine. And similarly, do another one. Negative cosine should go to negative of the derivative of cosine, which is negative sine. So those two negatives are going to cancel out, and I'm going to get sine again. And now I've looped back to the start. So this guy goes to here, right? So then I can see that I've completed a loop. That means that every fourth one, I get back to where I started. So for instance, immediately I can tell, f of 20, the 20th derivative of sine is sine. So this is because 20 is divisible by 4, right? And then, f, the 22nd derivative. Well, what should I do? I should look to the second thing in the loop. So it's this one, right? So it's negative sine. And then you can go overboard and do a really big one. So let's do just picking some random big thing, 107. The 107th derivative of sine. Well, got to see where it is in the cycle, right? 100, that's divisible by 4. 104, that's divisible by 4. So I must be 3 into the cycle. So that's this one, negative cosine. Because 107 is multiple of 4 plus 3. Yeah, so that's sort of a fun thing I wanted to highlight. It's good to think about. And the second thing is I wanted to show you one of the things that these small angle limits are useful for. So this is going to supplement some of the questions in the homework. So remember, the small angle limits are basically what we can approximate sine and cosine to be when the angle is small. So this small angle limit is 1, and remember the cosine small angle limit is, let's see, cosine theta minus 1 over theta is 0. And this is meant to be interpreted as, well, if we multiply this whole thing through by theta, then we're going to get sine theta equals theta. So that's a vague thing to say, but you should interpret this whole thing to mean is that approximately sine theta is equal to theta when theta is very small. And similarly, this one, if you run the same kind of argument, theta goes up here, but you still get 0. So what it's saying is that cosine theta minus 1 is approximately 0 when theta is very small. And you rearrange that a little bit, and you see that cosine is approximately 1 when theta is small. Okay, but what does this do for me? So here's my example. So the first example is let's have something slightly more complicated than theta. So let's have like limit as x goes to 0 of sine 7x over 7x. So what I'm going to do there is I'll say, well, let's make a substitution. So substitute theta as 7x. And then I've got to think a little bit about the limiting process. And what I want to say is that x goes to 0 is the same thing as theta goes to 0, because this is such a simple linear function. So with this substitution in place, I can substitute the limit, I can substitute the 7x, and that's the limit we recognize. So this is a very general kind of idea. Like, if I can plug in something here and I see the same thing on the denominator, the limit's going to be 1. So let's play with that a little bit, like do something a bit more complicated. Right. So maybe let's remember to carry our master limit over to the next page. So it's all meant to be based on this. And so the slightly more complicated example. So what if I were trying to find the limit as x goes to 0, sine 6x, say, but this time divided by 6 instead of divided by 6x? Well, I've got to work with what I know. So we know that the limit as x goes to 0 of sine 6x over 6x is 1. So that's from this reasoning from the previous slide. So that's from this kind of argument. And so what I want to do is leverage this fact. So what I'll do is I'll compare this expression to this expression. And I see that to get from this thing down here to this thing, I must have multiplied by 6. So I'm going to multiply by 6. I'm going to get 6 times the limit x goes to 0 sine 6x over 6x. And if I do multiply by 6 on the left, I've got to multiply by 6 on the right. And now I use one of the limit laws. One of the limit laws says that a constant can go inside. So that's telling me that the limit x goes to 0, I'm going to get 6 sine 6x over 6x is 6. But now I get some cancellation, of course. That's what the whole goal was to be. And so then I'm going to see exactly the expression inside the limit that I wanted to see. So after this cancellation, so this is how I can conclude that the answer is 6. Okay, so that was that's a nice one, but let's do a slightly harder one. So similar idea though. What if you presented with something a bit funnier? So let's say limit, we want to find the limit as x goes to 0 of 2 sine 3x over 5x. Okay, so we've got to think what's in charge here. So the thing we know about is this expression on the left. And so we're looking for this, what's inside of the sign here. So 3x is the thing that needs to be kind of pulled out of this 2 and this 5. So I've got to think like, here's the thing I know. I know that the limit as x goes to 0 of sine 3x over 3x is 1. And so I'll do this comparison again. So remember in the previous question, I looked at this thing and said, aha, multiply by 6 to get this thing. It's a bit more complicated now, so I've got to think like how to get from this thing to this thing. So I guess on the numerator, I'm multiplying by 2. So let's record this. So I'm going to multiply by 2 on the numerator, and on the denominator, to get from the 3 to the 5, well, I've got to multiply by 5 and divide by 3. So in other words, multiply by 5 over 3. So limit as x goes to 0, sine 3x, 3x. So this is, again, what you do on the left, you've got to do on the right. So this is going to be 2 over 5 divided by 3. And let's make this a bit nicer. We'll multiply the 3 onto the numerator and the denominator. So this is going to be 2 times 3, 6, and then the denominator gets the 5. Okay, so again, constant. It's going to hop inside the limit by one of the limit laws. And we're going to see limit as x goes to 0. So let's start calling this thing 6 over 5, because that's a bit shorter to write. So we'll have 6 over 5 sine 3x over 3x is 6 over 5. And I mean, the reason we wrote 6 over 5 in the first place was to transform this expression into this expression. So I think I'm just going to say, sort of by the construction of this fraction, the whole reason we picked it was because it's going to turn this into sine 3x and then 5x is 6 over 5. So hopefully you can sort of see the pattern there. We've got to use this angle, this is the theta, and then we've got to work out how to get from the known expression to the expression in question. Okay, so maybe I wanted to do something that wasn't exactly like these kinds of examples. But so let's think. Final example. What if I want to take the limit as x goes to 0 of x cotangent x? I don't know any small angle formulas to do with cotangent off the top of my head, but I do know stuff to do with sine and cosine. So let's write out the definition of cotangent and see if we can see something. So cosine over sine is the definition of cotangent, and then multiply by x. I guess I'll put the x on the numerator. Okay, now what I'd like to see is the small angle formula. I'd like to see this sine x. I'd like to see an x down here. So to achieve that, I'm going to introduce it. So this is going to be the same. Limit as x goes to 0, x cosine x over sine x. I want to divide by x on the top and the bottom. So on the top, we're going to get some cancellation. So this is going to cancel this. So we're going to get limit x goes to 0, cosine x. And then on the bottom, we see the thing we were shooting for, which is sine x all over x. Right, now we know some limit laws. So this is a quotient of two functions. We know a rule about limits of quotients. We can take the limit of the numerator and the limit of the denominator separately and then divide through. This is the one you've got to be careful on, right? Because if you try and do this when this limit is 0, you've just divided by 0, which is the cardinal sin. So we're in good shape though, because this limit is 1. That's the small angle limit. And so we're going to get 1 on the denominator. And in the numerator, well, cosine is continuous at 0, so we can just plug it in. And cosine of 0 is 1. This is 1. So that's another slightly different application of the small angle limit. Okay, that's about all I wanted to say.